Okay. So would anybody like to volunteer their recipe? Right. So we got the first bid is on step NZV. Oops, somebody else is typing. We have also step ZV. Good. Both have thumbs up. So the answer, NZV is not bad. My intention would be zero variance. And let me explain the difference between them. So here's what we need to run this. So think about this. Let's get rid of this. We're going to not other things. And then we'll create dummy variables. So the difference between step ZV and step NZV is that ZV means zero variance, right? So what it would do is after you make dummy variable columns, it would look to see in your training set, are there any columns that are all the same value? It doesn't matter what the value is, whether it's 1 or 17 or A. It looks for anything that just has one unique value, and then it would remove that from the training set. So that's what zero variance means. The reason we created, and this I did this in Carrot a long time ago, is I had a lot of instances where we had a data set that was like 999 ones in or zeros in a single one, right? And so when you have a data set like this, you know, if you look at the that and you spell the function name right, oh wait, I did it wrong. Rep. Oh, sorry, I got the numbers wrong. 0.99. So we look at a table of that, it's actually not zero variance, but it kind of is, right? So NZV stands for near zero variance. And what near zero variance is we have some rules that you can adjust that try to pick off which predictors are almost like really close to being, you know, very sparse. And so, you know, the people I worked with, especially the chemists I worked with, would have like sometimes thousands of columns like this that were nearly zero variance. And, you know, we would get in these discussions about, but you know, together they might actually solve the problem. I'm like, yeah, no, like that single one in that column is probably going to have like undue influence on the analysis. And I felt like it caused more problems than it was worth. So the difference, in effect, in this case, the difference between NZV and ZV is NZV will probably remove more columns than ZV would. Again, if ZV wouldn't remove a column like this one, so either is really fine, but my thoughts originally were ZV. So how would we adapt this recipe? Somebody has it in the notes step. Let's just say ZV, but you could have done either. And then you need to specify. So what you could do is you could say all predictors and then get there. Another thing you could do is if you wanted to just do this on the neighborhood values, then, you know, as I mentioned, the names of these values are going to be like neighborhood underbar and then the level. So you could do starts with, did I spell it? Why is it not seeing that? Oh, okay, yeah. And then do like neighborhood underbar. And so if I do that, and if I just wanted to select or like potentially filter out the resulting dummy variables, I could do it this way. And now one of the reasons I bring this up is the reason we had things like all nominal or all predictors is with recipes, sometimes when you're designing them, you don't really know what the columns exactly are going to be, or even sometimes how many of them you're going to have. And this is a good example of that. Like if you use step other, you know you're going to get columns back that are like neighborhood, underbar, or something, but you don't know how many of them you're going to get because it depends on the data and the threshold you use. So in some cases, you end up running recipe steps on columns that don't exist yet. We'll have another example of that when we do PCA a little bit later, where the number of components we use might vary. And so if we want to do anything after that, we need to find a way to select those steps, even though we don't know exactly, like we know how to, based on their names, we'll know how to select them. But if we wanted to like type them out, we wouldn't know whether there would be, in this case, like 7 neighborhood dummy variables or 12 if we use step other. So that's the nice thing about these selectors and recipes is you can select for things that don't officially exist yet. So there you go. So let me put this in Scratch. Okay, well done. I will try to make the next one more difficult. All right, so let's talk about a few different examples of like pre-processing or feature engineering stuff that we might want to do and how we can do them in recipes. So interaction effects are things that we are pretty common to use. So here's a plot that might look familiar because we looked at it early on yesterday. And so what we do have here is we have sale price versus the year built. And we looked at the same thing for general living area, where in terms of sale price, we have like, houses are a little more expensive. On average, they get a little bit cheaper over time, and then they get more expensive again. So if we were modeling this, we might want to do like a quadratic component or a spline or something here, because it may be beneficial to not just fit a line through this that maybe wouldn't fit all that well. But then, I talked about like doing random selections of columns in a data set and then plotting them to look at them. And in looking at this data long enough, when I figured out that maybe this isn't quadratic, maybe there's another factor that's affecting the relationship here. So it turns out that if you look at whether the house has air conditioning or not, you definitely have like no year effect when there's no air conditioning. And there's not that many houses proportionally in Ames that don't have AC. And then if you look at the year built for houses with AC, it's linear. It's more linear, but you still might want to have like a quadratic effect maybe in the tail here. But definitely we know that there's a different relationship for no air conditioning than there is for air conditioning, or whether this one's linear or not. Doesn't really matter. We know that they're not the same pattern. And so this is a really good definition of an interaction effect. There are others in this data set that you can find and discover that have a significant effect on the fit. So it's generally speaking a good thing to look at. I very often find them by looking at ggplots. And in the feature engineering book that we linked to yesterday has some algorithmic ways to discover interactions in data sets. And so if we were doing this using LM, what would we do? Well, we would build a model, let's say, with the main effects, meaning there's no interactions, and then build a second model with those same effects plus the interaction. And the interaction here would be, if we were using LM, be year built : central air. Now, central air here is a factor with values of y and n. And so, again, what model.matrix does is it converts these dummy variables to one dummy variable for a y, central air equal yes, and then it multiplies that by year built. And so that's what it does. It adds that term to the model. And if you build these two models, you can do what's an ANOVA, which is analysis to say, okay, how much did that additional interaction term help the model, and is that sort of statistically significant? So did we reduce the error in the model enough to where that extra column is worth it? And if you do that ANOVA analysis, the p-value is very low, which means, at least from a statistical perspective, that this interaction definitely helps the model. by accounting for more error than it would without, from a statistical sense. So we know it's a real thing. Like we might want to still have a quadratic term in here somewhere, but it's definitely at least worth having this in there. So this is how we would do it in base R. How would we do this in recipes? Well, we have step interact. This is the only step that has a slightly different interface. And the thing is, what it does is it wants you to have created dummy variables before you define your interaction. So as I mentioned before, model.matrix does this automatically. It will make dummy variables for you when you have this interaction. We don't do that in recipes. So what you would need to do is you would need to take all the dummy variables for a variable and then say they have an interaction with something else. And so in this case, central error only produces one dummy variable. But let's say we had a dummy variable or an interaction with neighborhood. What we would say is starts with neighborhood and then colon whatever else we want that interaction to be with. And let's say it was a three-way interaction. We could say starts with neighborhood, colon year built, colon, I don't know, general living area, or whatever the third term that interaction would be. So that's one difference here for step interact is you have to, if you just give it central error, it will yell at you and say, hey, we haven't made dummy variables yet. I'm not sure what you want me to do here. So that's one difference for this step. Another difference, and this is the only step that's like this, is you have to put a tilde in front of it. We tried and tried to get this to work so that you didn't have to do this, but you do. So when you do interactions, you say tilde, and then you can give it any number of interactions that you want. So if there's another set of interactions that you want to declare here, you can say plus, and then give the variable 1 colon variable 2 list that way. So you can have as many of them as you want here. And so this is what we would do to define an interaction. Once we prep it, let's look at what the columns are. Again, what base R would do is would smash those basically names together. And I think I'm pretty sure you can change this, but what we do is we use a underbar X underbar to denote an interaction effect. So this is the one column that gets produced by that interaction step. It is the product of the central error dummy variable times the column for year built. And that's how you would create an interaction effect. So why not use this recipe specification? I don't think that'll work. Let me try it. So there's a question about why not just do what you would do in base R, year built times, was it central error? There's more than one answer here, but the answer is it says, yeah, you're not allowed to do that. The thing is, we don't want to implement the full formula method in this initial recipe step. We don't want you doing calculations in this part. The recipe formula here, when you call recipe, is only supposed to pick off the variables that should be used. And so by using this interaction effect, what you're doing is saying like, oh yeah, make me dummy variables. And so then if that's built into the formula, we'd need to just do model.matrix throughout the whole thing, because we would need to know how to make dummy variables for everything, or inline functions. And so again, this is the same thing as a similar error that you would get, for example, if you try to do, let me get back here. Let's say you didn't do that and you just did this, but let's say you did like log here. It will complain in the same way. It says you're not allowed to use inline functions. So it might seem more like we're making it more difficult, but in a way, we don't want anything to really happen here calculation-wise. We want that to all happen in steps. So that's the answer. It's a good question. All right. So we'll talk about...
There was one kind of interesting question here about, do interactions help when using tree-based methods?
Oh, yeah. Well, instinctually, I would say no, but I wouldn't say never try it. And the reason I would say no is that trees are like pure interaction models. So if you were to write out like once you fit a tree, which is a bunch of if-then statements, if you were to try to write that out as like a prediction equation, it would be the product of a bunch of like dummy variables. And so like the first split of a tree would just be like, if you're built greater than 1940, then this, else than this. But then as soon as you go to a second level of splitting, that's a pure interaction on each side of the tree. So like if you read the elements of statistical learning and things like that, they make a big deal out of saying that tree-based models with a depth more than one are just interactions all over the place. So I would say probably not worth doing. I would let the tree figure that out. But, again, it's one of these things where like sometimes I'll try things. It probably wouldn't hurt, but I'm not sure it would really help because the trees would work that out anyway for you. Yeah. I'll wait another minute. There's some more typing. Several people typing. Too much of a tangent. Feel free to defer. Do recipes allow for other contrast coding? Yes. So what if you didn't want to do the typical contrast? There's a couple things you can do. Let's say you want to do, let me go back to this. So let's forget about step other for a minute. Let me just do basic dummy variable step here. One option you have, so remember there's 28 levels of neighborhood. What you can do is if you want all the dummy variables, there's an option here to say one hot encoding is equal to true. And that will give you a 0-1 column for everything, right? So one hot encoding is, instead of you having like, if you have C levels, instead of getting C minus 1 is what we almost always do. But if you want to get all C 0-1 columns, you can get that through one hot equal true. Now I'll back up, and the question is like, what's another contrast encoding? There are other ways to take categorical variables and make them into dummy variables. And so the one that we typically use when I was taking statistics, it was called a reference cell parameterization, where one of the levels gets left out and you get 0-1 values for everything else. There are other things called Helmert, which is a really weird one that might have like ones and negative ones in certain columns. So there's a bunch of different ways you could encode those dummy variables. They don't always have to be 0-1. So if I do contrasts, I think it's, yeah. So if you just type the main help page's contar, stands for contrast, sum, what you get is a list of possible contrasts that are built into R. So for example, like the Helmert, I've never understood why anybody would use this, but if you had 4 factor levels, the Helmert contrast would give you 3 indicator columns that have negatives in some case and integers otherwise. The one that I think we use the most is I think it's treatment. So the first level gets no indicators, but the others get 0-1s and so on. So, okay, Helmert's good for ordinal. So what you can do is if you want to use something besides one hot, I think this is in step dummy. What you can do is you can use a standard R method for setting what contrast you want to use. So I think that's in here somewhere. To change the type of contrast being used, change the global option. So for example, if you look at the options that are there, one of them is for contrasts. I can't remember the name of it. It's just contrast. So if I do options $contrast, it gives me a list back for what it should use for unordered categories and ordered categories. And so if you look at the help for this, you can see there are ways to reset these. And so you would do that before and after running recipes to get the proper contrast method built into recipes that you're using. So yes, you can do that. And if it's one hot, then use the option here, but otherwise you could use whatever you want to use.
There's a really great question here that gets at the heart of what recipes, like one of the reasons we use recipes, asking about like baking on the test set and like what happens when you apply something to the test set. Like we did something on the, the training set, and then we do it on the test set. Like what's going on there? So that really highlights, I think. So it's good. I think this is a good thing to clarify.
Right. So
what is prep doing? And then what happens when we bake?
So what prep is doing is it's estimating everything it needs to on the training set. That's the primary thing that it does. So like with step other, it's figuring out, like in your question, like which one of those levels should be dumped into other. So let's maybe look at that for a minute. Let's take so I'm going to answer your question, but I'm going to show you something that'll get you there a little bit faster. So here's my recipe. The prepped version of it is where, it's up here. So I prep it, and then, I have all my recipe steps. The third step, I'm sorry, no, that's the wrong one. Hold on. This is the one I want. So this is the one that was in the notes, and I prep it, and I have step other, right? All this is estimated from the training set. So one thing that'll come up later is we have tidy methods for these things. And so if I want to see what neighborhoods were left out, or actually which neighborhoods were retained, I can run the tidy method on that and tell it, there's two different ways to do it. I can tell it the step number that I want. Like I want to look at number 2, which is step other. And then what this tells me is, this tells me which ones are retained and everything else gets dumped into other. Okay, so these are the ones that had fairly high frequencies in the training set. So when you let's say you were to bake the training set, regardless of whether you bake the training set or the test set or any new samples, it's going to take the things that it estimated from the training set and apply those same changes to all the data, no matter what, whether the training set or the test set. So when you run the training set through, your factor level would only have factors for these levels in the retained column plus another one for other. And then the same thing would happen in new data or the test set. They would all be changed exactly the same way. And those changes are estimated from the training set. And so this might seem like, why would you do it that way? It's important to realize, I'll give you 2 examples of this, that the training set data is what's given to your model. And once it's sort of embedded into the model, everything else has to be consistent with that. So for example, if the model only has like these 8 levels plus other, it has 9 levels, and the test set is giving something other than, like after it's been baked, something other than 9 levels, then now you have like different data structures between what the test set had and what your model thinks it should have, right? And so that would cause a failure. You always want to make sure that all of your pre-processing is always based on the training set and then applied to the other data, okay? Here's another example to maybe demonstrate like an edge case as to why it wouldn't work if you re-estimated the pre-processing on your new data. So let's say we're going to center and scale longitude and latitude. So centering means subtract off the training set mean, scaling means divide by the training set standard deviation. And so imagine that if you get like a couple of new houses, let's say 3 new houses that you want to predict, or actually, no, let's say you have like a single house you want to predict. If we try to re-estimate the mean and variance, there's 2 issues with doing that. Is the data that you're using in the test set may not be from the same population as the training set. So you're centering and scaling based on the new data or the test data might be like apples to oranges. And so the parameter estimates in your model are based on the scaling that was given to them in the training set. So them having a different scaling would actually give you, it wouldn't cause an error, but it would actually be giving you the wrong numbers, because this is expecting the test set is on one scale, but the training set's on a different scale. So you want them to all be like on the same scale in that instance. And another obvious reason why, like when you think about it, that centering and scaling wouldn't work on new data by recalculating on new data is, imagine you only had one single house you were trying to predict. The standard deviation of that's 0, and you can't divide by 0. So these are like good examples that demonstrate that you have to have apples to apples when it comes to pre-processing, and all those apples sort of need to come from the training set. So an example you're talking through, does that mean the unknowns, new levels, only in a test set, are just ignored, but bake won't fail? So it depends on how you do it. So if you do like step other, I don't believe they would fail, but a better approach is we have something called step novel. And that is built for situations when you have a new, when you know ahead of time that there's a good chance I'm going to have another neighborhood or new value of factor coming in. So one way to deal with this is to not build into an other, but build into an extra level called new. That's the default value for it. So that any new things that come in, like all the dummy variables you had before, would stay the same, but anything new would come in and get lumped into this new level. It's really, it may seem subtle. It's different than what other is doing. Other is reducing the number of factor levels, whereas step novel is saying, well, keep it as it is, but let's add another level that will just dump into anything that we don't know goes into that new level. And that way you don't cause problems. Those new levels still won't really have an effect on the model, because their data wasn't there to begin with when you built the model. So, but it just stops it from failing. That's the simplest approach you could take. I mentioned this thing yesterday called feature hashing, which is another way of dealing with new factor levels that are going to come in. So we have a recipe step in another package called the embed package. So if you were to like load step embed, the embed package. And then do step, was it feature hash? Yeah, step feature hash. You can use this to create dummy variables. There's pluses and minuses with this. I talk about this in the feature engineering book. It's good when you have a lot of levels. So imagine like having a model where zip code is in the model, and zip codes, I think there's like 20,000 zip codes in the US. This is really built for those situations, but it can also handle when a new zip code comes into being, then this would not crash. But there's some kind of not great properties about dummy variables created using this feature hashing thing. So it's not my first choice, but it's something that you could use. And also embed, there are these things that we call likelihood encodings. For example, that do something other than dummy variables. I won't go into it here, but this is another thing you could do to handle new levels. These ways to handle dummy variables also can handle situations where a brand new level comes into the test set. And again, this is all outlined in the feature engineering book. So it's hard to like really go through a lot of it here, but there's a bunch of different ways you can handle it. But we definitely, the main point is all of our pre-processing, no matter whether it's this or anything else, has to happen on our training set, and then get applied to everything else just to make sure we're apples to apples and everything. Okay. Okay. So this is really important, the next section, and it's about skipping steps. Like, what would you do, or why would you want to skip a step, and what do I mean by that? So let's think about this in the current recipe that we have. I gave you this very nebulous comment earlier, ominously saying there's something kind of off in doing log of the outcome in a recipe. So like when you're building your data on a model, you know what the outcome is. So like this is a data set, you know, x2 here is like a factor, but everything else is a number. And so we have our outcomes in blue and our predictors in this reddish color. And so we build our model on the juice data set. We know that the outcome is there because we have the training set. But what happens when we go to make predictions, right? So we go to make predictions on a new house. I don't know, you know, I'm not supposed to know what the outcome is. So the thing is, you don't have that column anymore. So if you say step log on sale price and try to execute this on a data set that is just for prediction, it doesn't have the outcome. And so it will actually throw an error and say, I don't have sale price. I can't log it because it doesn't have it. So when I talked about how tidymodels handles data, when I said it compartmentalizes things, that if you had the data frame aims test, even that's a test set, and we have that column in here, but you know our predict methods are written so that they don't require or expect the outcome data to be there because they are not supposed to use the outcome data, right? And so the thing is, even if that's in the data frame, we do not keep it. We know what variables are the predictors, and those are the ones that are given to predict. So when it goes to process the recipe, to process the prediction data, it knows to do step other and step dummy and all this stuff. But anything that uses the outcome, it fails on because it doesn't actually have the outcome because it's not supposed to have the outcome. So there's two ways of going about this. The first thing you can do, and the better thing to do would be to just do the transformation ahead of time. So what we would say is instead of doing this, where we have the aims data, sale prices, then the natural units, we do the training and testing. What we think you should do when you're doing like a simple transformation on the outcome is to do a real quick mutate. Oops, you spell it right. So what we would rather you do is just pre-log the data before you do anything else. And that way the training and the test set has the data logged and you don't have to add that to a recipe step. The recipe step, for the most part, and I'll show you an exception in a minute, should not really use the outcome data directly, not like do calculations in the outcome data. And again, the reason for that is because you're not supposed to have it around after model fitting is done. And so this will cause errors here and there because we don't give it, you know, to the prediction method because it's not supposed to be used. So the first thing we would say is we would rather you pre-transform the outcome data prior to the recipe. In fact, prior to the data splitting, so you know it's the same way everywhere. That's really what we think you should do in this particular instance where we're like logging the outcome. So that's point number one. Like better to pre-log than to use step log on the outcome. Now, there are other recipe steps that indirectly use the outcome data in a way that is fair. So let's talk about something called downsampling. So downsampling is a situation when you have a classification data set, like this one here on the left, where you have like an outcome that's categorical. And let's say it just has two levels, A and B, and then have a bunch of A's, but like only 3 B's. So there's like a really low event rate in my B's. So one way that you can deal with this is you could do something called downsampling, where instead of using all the data in the model, you randomly take the majority class and sample it down to be the same size as the minority class. So the minority class here is B. We only have 3 levels. And so if you downsample the data, you take the training set, and then you only select as many A's as you had B's. So it's a smaller data set, but this, oddly, this can give you better results if you don't have a huge class imbalance between the outcome levels. So the thing is, when you're modeling, we're using the outcome data here, right, so that we know what this downsample. But when we get new data, we don't have the outcome, and we don't want to sample that differentially anyway. We would only do this type of operation on the model data, not on the prediction data. So here's an example where we wouldn't want to do this ahead of time, like I advocated with the log of the outcome. What we need to have is a way to tell steps to do them only on the training set, but not on new predictions. And this downsampling is a good example of when you would want to do something like that. So what we have, it turns out, is if you look at the help file for all these steps, like I'll even look at step log, all of them have a mandatory outcome of skip. And they almost all of them default to false. And what skip means is, should I not do this on new samples? So should I avoid this particular step when I have new samples? And so let me go back to this downsampling thing that we have. Let's see, step. Oh, it's in a different package. You don't have to use this package right now, but we moved it into a package called themis. So if I look at the help file for step down sample, okay, it's both places. We'll look in the recipes. It has its skip set equal to true. And what this means is it will downsample the data used for modeling that you get back from Juice. But whenever you use bake, it will not execute this step on new data that you would get through bake. So, so there are situations where you do want to skip certain calculations on new data. And then the option to do that is to skip equal true. And what we've done is we've gone through all the steps that this would happen and defaulted their skip equal to true. So generally speaking, you don't have to worry about setting this to be true or false. The defaults are cover like all the normal situations that people would find themselves in. I'd be kind of scared if people were modifying this to be true in a lot of cases. So this is something you shouldn't have to modify. But you should know that there are some steps like this downsampling where we don't want to apply, we only want to apply it to the modeling data, but not to the prediction data or to the test set. So yeah. So here's our new sort of pipeline for our data is we're going to amend our recipe to get rid of step log because that's not really a good way of doing it. We're going to pre-mutate the sale price to be in log units and then make sure that goes through with the splitting data and in the recipe doesn't have step log in it. And that is the preferable way to do things in tidymodels when you have just a simple transformation you're making on your outcome. So there's another question I'll talk about in a second, but any questions on the skipping and the pre-logging? And hopefully I've done a good job of rationalizing why that is the case. So if I haven't, let me know. Okay, so the other question is, we discussed creating new levels for NA values, in particular column data, in particular column to deal with missing values. These will hopefully be rather sparse. Do these get caught by step other, or is there another way to retain the specific level? Right, so we have yet another recipe step to deal with this called step unknown. And what it does is step other wouldn't know what to do. So if you did step other and then gave it a missing value for the factor, it doesn't, I mean, it literally doesn't know whether it should be other or not. It could have been for like North Ames or it could have been for something else. It has no way of knowing. So one thing you can do ahead of time is do step unknown. What that does is you can maybe place that in the recipe before you do anything else. So if I was worried about that for neighborhoods, what I could do is maybe here, this is for the breakout example. What I could do is I could do step unknown for neighborhood. And what it would do is when neighborhood has a missing value, or before, what it would do is something similar to what step novel does, is it creates another factor level called unknown, and anything with a missing neighborhood value gets lumped into unknown. And then you can do whatever you want. You can still have step other, you could have step dummy, anything you want to do with it. But if you have a missing value, none of the other factor-oriented step functions know what to do, because the thing about missing values is it could be anything. So so I would advocate the first thing you could do is you could say step unknown, convert it to another factor level. An alternative would be to step impute, mode impute. So what you could do in this step is you could estimate the missing value using the most prevalent value in the training set. So if North Ames is the most prevalent neighborhood in the training set, if you wanted to use step mode impute, that would be the mode, the most commonly occurring thing, and it would impute any missing data to be the one that's most likely, which in this case would be North Ames. So these are the two things I would advocate using for missing data in factors, like an imputation method like this one, which is very simple, or a step unknown. Hopefully that answers the question.
It sounds like there's that Shuro has an interest in really customizing the other in step other, what goes into the other category. For example, the thing that comes out of step unknown, the new value, not having it get into the other bucket, like being like, oh, those step unknown things, I want to keep those, and not have them go into step other, even if they're a small. And
because you would think they would be a small rate.
Yeah, right. I'm trying to picture some way to order that.
Does step other, would it just completely ignore the
NA values?
If it just ignores them, you could run that first.
Right.
And then do step unknown.
Yeah, because it would, yes, because so if you ordered them where you did step other first, if it's NA going in, it's still NA coming out. And then, so it wouldn't get captured by other, I'm almost positive. And then you can do any of these things to impute it to be what you think it should be. Yeah, that would be the solution. All right, a very good question was just added. Will step log fail for new data if skip is set to true? Yes and no. Depends. Here's what happens is if I set this to true, it will not fail when I go to get new data. But here's the problem is if you're working on the test set, then the problem is your predictions are going to be on the log scale, but your observed data are not going to be.
It's like for kids, little kids.
So the problem is we're going to talk about the tune function, like the tune package and tune grid and things like that to do model tuning. So this will not cause an error. It'll give you really bad performance because, for example, inside of tune, when it goes to compute the RMSE, the predictions are going to be log 10, but the observed data, because it was skipped, are not going to be log 10. So that would get you far if you're not doing any of the tune functions. If you're just using like recipes with like base R or non like tuning functions, that would work. But in general, and this is one of the reasons why we think it's better to pre-transform them, because you would have like two different scales of your outcome being used during model tuning. So yeah. Yeah. And if you really wanted to see that, just go into the tune package. There have been a couple bug reports where people have come across that. I'll be honest, like I thought about this, but I didn't think about it enough. And it's something that we had not until recently highlighted a lot in our training materials. So it's an easy trap to fall into, and we're rewriting a lot of our training materials to talk about this so that people don't fall into it. We haven't done a good enough job of explaining this. So, yeah. From a workflow perspective, would you typically have a different recipe for different model specifications? Yes. So there are some, we'll talk about this a little bit more. There are some pre-processing methods that are really specific to certain types of models, like dummy variables. Like you don't need dummy variables for like random forests and tree-based models usually. So, you might want to not have a recipe that does that. Some, for example, I'll talk about this in a second because there was another question about imputation. Like tree-based methods like CART or C5 can handle missing data in the predictors. Most can't. So you might, if you have missing data in your predictors, you might maintain a recipe that has imputation in it and a separate recipe that doesn't for the models that don't need it. So you don't need to have like a one-to-one match of recipe per model. But at the same time, when I work, I tend to end up using, I don't know, I'd say like anywhere from 50 to 75% of the time, different recipes for different models, just based on what they need. So like, the question about interactions in trees, like, if I knew of an interaction and I was using LM, then I'd want that in there. But if I were giving that to a tree-based model, I wouldn't have that interaction in there. So yeah, I think there's a good rationale for, it doesn't always have to be the case, but usually for some models, they're going to have their own recipes.
Other examples of that are like indicator variables and centering and scaling. Those are things that come to mind that you're like, well, no, like I would or I wouldn't do this depending on the model.
Yeah. One thing that we're doing is we have a tidymodels book that we're writing, and I'm really hoping in the next month to get that, at least the first couple of chapters out released. And there's an appendix in that book that has recommended pre-processing for different models. And so you could look through that and say like, oh yeah, okay, these ones, like, I'd probably do the same processing for a neural network and a support vector machine in LM. But so you might have like one recipe for that batch of parametric models, but then have another recipe for all the tree-based models and so on. So they don't have to be like one-to-one. There are a bunch of models that have sort of the same requirements, and you can do the same thing, but it's not really, they don't have to be different, but they often can't be the same. And then there was a question about recipe functions for imputation of numeric data. Yeah, we have a couple of them. Julia linked to this section on imputation. So I think there's at least 3 of them there to do that. Okay. All right, so going forward for AIMS, we're going to use this as our basic recipe where we don't have step log. We're going to pre-log. Right. So now we're going to shift over to a different type of pre-processing that we can use. We're going to continue on with AIMS, but there's a nice data set we can use to demonstrate this thing called principal component analysis. So I want to talk about what PCA is, because it's an incredibly useful tool, and also how you would do it in recipes. So let's take this little toy example. This is real data. The actual data set has like 50 or 60 predictors, but I was looking at this one day, and here's 2 predictors in this data set. I just call them A and B. It's a 2-class problem, so I'm trying to basically differentiate the red circles from the blue circles. And the thing is, in this data, if you were to like do ggplots and things like this, it kind of seems clear that you can differentiate them, where like if you drew like a diagonal line here or some sort of line like along this axis, that you could probably do a decent job separating the reds from the blues. But the thing is about this data is if you did like a box plot of predictor A for classes 1 and 2, the distributions sit right on top of each other. So predictor A itself doesn't really have any effect. If you did the same thing for predictor B, you'd find complete overlap between those 2 distributions also. So it's a weird and interesting problem where you have these two predictors that it's not really an interaction, but their effect on the outcome, you have to have both of them for it to work. If you try to just use predictor A or predictor B, you can't really separate class 1 from class 2. So, when I look at this, this might be hard to do over Slack, but like when I'm normally teaching this, I would say, well, we have these two predictors. They're highly correlated, right? The correlation, I think, is like 0.8 something. They're both right skewed. So we have a lot of data at the left part of their scale and like these trailing tails to the right. So they're both right skewed. If we were to add this to like to GLM to do like logistic regression, our performance would be somewhat diminished by the fact that these two predictors are highly correlated. So we do take a hit in performance when we have correlation between the predictors, and it's pretty high here. So we're in this conundrum where like, well, I don't like that they're correlated, but I need both of them. Either one individually doesn't work. So like, how do I do this? Like, how can I make this a little bit better? This is not a rhetorical question. Like, when you look at this scatter plot, is anybody listening have any thoughts about like what they would do in this instance with these two predictors? Like, are there any transformations or any, like, what would you do? So like type in if you have any thoughts on this. It's not a trick question. It's kind of a hard question. Somebody's typing. I should have like the Jeopardy music playing in the background while people are typing. Try several variants reducing transformations. Start with logs. Good answer. I would go back one slide. That's an excellent answer too. Okay. There's a couple things we can do here. The first thing we can do is we could, as was recommended, look to do transformations. And to be honest with you, when I see skewed data, the first thing I think is log. It turns out that you can estimate a transformation, that there's this thing called the Box-Cox transformation that would encompass things like square root, log, inverse, and so on. And the cool thing about the Box-Cox transformation is it statistically estimates the right transformation. So it has like this parameter tries to estimate we typically call it lambda. And if lambda, for example, is estimated to be around 0, that ends up being around the log transformation. And if lambda is equal to 2, it's like an exponent. If it were 2, then you would square the predictor, or if it's -1, you would invert the predictor. And if you were to run the Box-Cox transformation on each one of these predictors, you would get a transformation that's about -1, meaning both of them would probably be inverse. And so the plot here that I'm showing is where I've inverted, 1 divided by A and 1 divided by B, and it's better, right? So the one thing it does is it gets rid of them all being jumbled down here. It's not as right skewed. So that transformation tends to resolve skewness. And this is definitely better. But again, it's a situation where, yeah, I need both of the predictors still, and they're still highly correlated. So it does kind of solve the skewness, troubles, but not really the problem of how to differentiate these the classes better without having correlation. So this helps substantially, but it's not probably as good as we could do. And so if you were to do that, if you had this data set, and I think in the code we show how to get it, there's a step called Box-Cox. When you prep it, it would, there's 2 predictors here, so all predictors really A and B. What you would do when you prep it is it would run this transformation and estimate what that transformation should be, and then transforms the data back. So you would use that, or a recipe like this one, to go from having data that looks like this, and then once you push it through bake, it looks like this. So that's how you would do this box cost transformation with these data. But again, it's not really getting us everywhere we want to go. And so the problem is really one of correlated predictors, that there are a lot of cases where you have many predictors that are kind of measuring the same thing. And so if you think about like the Ames data, we have like lot area and general living area. We have the first floor square footage and the basement square footage and the number of baths. And those are all kind of like different proxies for the size of the house or size of the property, right? So if your general living area is high, as that increases, probably, not always, but your first floor square footage would increase. And if you have unless you have like a really, really big house on a really small lot, I would imagine that as general living area increases, lot area probably has a rough increase too. So, there's, in the Ames data, there's the potential for highly correlated data. It's not that actually bad in the Ames data, but just as a demonstration, that's what it does. There's a data set we'll look at in regression, which is about cars. And we have all these things like trunk volume and weight of the car and things like that. So there's a lot of times where we have these variables that are kind of measuring the same thing. And so what we want to do in some cases, especially when we're using a model that is very sensitive to correlation between the predictors, it makes sense to try to find a way to decorrelate the data. So the two places where I think this is the most harmful would be a neural network and a support vector machine. Linear models have trouble, like logistic and linear regression have trouble with this, but the term we use for correlated predictors is something called collinearity. That means that they're correlated. And collinearity is something that could really kill a neural network. And so we want to often try to find ways of getting rid of the correlation or neutralizing it somehow. So there's a couple of different ways to do this. For now, we'll focus on something called principal component analysis. But there's another thing we'll talk about in regression called regularization. So let's talk about PCA and what PCA is. PCA is called a signal extraction method because what it does is it takes your original set of predictors. In this case, we have two of them. But let's imagine for a minute that we have 100 predictors and they're all very correlated with each other. So what PCA does is it tries to take those 100 predictors and sort of make a new variable out of them, like a fake artificial variable that captures as much information about the original 100, but only in one variable. So that first principal component, that first new variable that you make using PCA, tries to account for all the interesting information in the 100 of the 100 original predictors. And so the way it does that is it makes sort of linear combinations of those 100 predictors. So the first principal component isn't one of the predictors. It's a combination, a linear combination of those 100 predictors. And so that first principal component using math captures as much of the first component as possible. And then what it does is it kind of removes the effect of the first principal component from the original 100. And then what it does to get the second component is it says, well, for whatever's left over, we'll make the second component account for as much of the leftover information that the first component didn't get, and so on. And so what you can do is, if you have really highly correlated predictors, let's say 100, you might only need 3 or 4 principal components to represent all the information or almost all the information that's in the original 100. So it's not like you're getting rid of features, but you're reducing the dimensionality of the original 100 to a much smaller set of principal components that represent different aspects of that 100. So it's a way to reduce the dimensions given to the model. You still need the 100 to compute all the principal components, but instead of giving it the 100 original variables, you can give it the smaller set of principal components. And what's really, really nice about the principal components, and this is the reason we would do it in this case, is that we guarantee that the principal components are all uncorrelated from each other. So if you were to calculate the correlation between the first principal component and the second principal component, it would be numerically 0. So what you can do is, by using these, you can extract the signal out of 100 original predictors into a smaller subset of principal components that are completely uncorrelated with each other. So you're making like an uncorrelated representation of the original data. And then you could give those components to the model and not have to worry so much about the problem of correlation. That's basically what it does. When I describe this to people, I think about like making a stew or something like that. I'm very food oriented. It's like you're boiling down those 100 things to get rid of the stuff that you didn't need into a smaller like set of variables that represent the same thing, just with a smaller size. There's some typing, so let me wait till I proceed. Is it possible to achieve higher accuracy with a smaller number of principal components compared to using all the data? Yeah, I'll talk about that in a minute. Let me postpone that till near the end of our PCA conversation. All right. So if you've never seen PCA, again, what it does is it makes new variables that are uncorrelated, and you usually need less of those than the original data set. So if I have 100 predictors, at most I could have 100 principal components. So the maximum number of components I would need would be 100, and that would only happen if my original 100 were completely uncorrelated with each other. So the amount of correlation in predictors increases, the number of required principal components goes down. So the higher correlation you have, the less components you typically need. All right, so this kind of recaps. Each component is uncorrelated with the others, which is very nice. The new variables, the new components, are linear combinations. So I still need the original data to get to the components, but I'm representing them differently. And again, you would do this to reduce the number of variables given to the model. And you would do this to fight this problem of correlation between your predictors. And that's why it's called a signal extraction method, is that you're extracting the information from the original data in a smaller set of signals. Now, for two-dimensional data, it's actually geometrically, it's easy to describe what principal components are doing. So here's our data. We see they're highly correlated in 2 dimensions. We've made it better by taking the inverse. What PCA is actually doing in multiple dimensions, but it's easy to see in 2 dimensions, it's going to take these data, have an animation coming up. We're just going to rotate them around, and to maximize the variation of the first component, it's what the first component does, is it tries to maximize the variation that it can extract out of the training set. All it's doing is it's rotating this cloud of points around its center to try to find the right rotation of the data so that variance of the data are maximized. So let me show you what that means. Is the new component is down here, and you can see this bar that is expanding and contracting. That's the amount of variation that the component number 1 is accounting for. So when our data is at a diagonal, like it is about now, the new component is not very wide. What we do in principal component in 2 dimensions is we're just rotating these data so that the new dimension that we project down to is as wide as possible. And that's basically what PCA does. So if I take this original data and rotate it to be in the principal component dimensions, I'll show you how to do it in a second, but this is what it looks like. So the first principal component has the widest range because it accounts for the most variation of the original data. And the second component has, since there's only 2 possible components in this case, whatever's left over. So again, the component is trying to account for information, and that's usually phrased as variance. And so the reason it's been rotated to be horizontal like this is that maximizes the dimensions of the first component. And since there's only 2 possible, it minimizes the dimensions of the second component. So what you can do in PCA is you can calculate what the percentage of the original data that you're accounting for. So I know from this data set, when we run the numbers, that this first component captures about 92% of the original information or the original variation that was in the data before it was rotated, and that the leftovers would be in component number 2, and that would be basically about 8% of the variation is in number 2, and 92% of the variation in the predictors is based on component 1. I will come back to this in just a second. So again, what PCA is doing in any dimension, but you can see it in 2 dimensions, is it's like rotating this cloud around its axis to it's trying to find the best way so that you can position the data so you don't need all the dimensions. Hopefully that makes sense. So how would we do this in a recipe? Using the data we had before, like where we box cock transformed. So this is what we had previously to show that we would get the inverse transformations. Now, PCA is chasing variation. And in the Ames data, we have, for example, some predictors that are in units of square footage, and we have other predictors that are like number of baths, which is like 1 through like probably like 3 or 5 or something like that. And they're all on separate scales. And then if you think about indicator variables, they're all 0 and 1. So what you want to do before putting the data in the principal component analysis is you want to center and scale the data so they're all on the same scale. Because if you don't do that, then what happens is the variables with the largest scale, like square footage, would end up inappropriately dominating those calculations, not because they're important, but just because they have the largest numbers in the data set. So an additional step we do before PCA is we run step normalize. That will center and scale all the predictors. And then we can run step PCA that will transform them into principal components. And so this is what a recipe would look like with PCA steps. We'll do it again for another example probably next week. But when another important thing about the mechanics of this is the original data are not retained. So again, PCA is trying to represent the original data with principal components. So if I come in with columns that say predictor A and predictor B and transform them into PCA, the new predictor columns are going to be called PC1 and PC2. Okay, so the names are going to be different because PC1 is a function of all the predictors, PC2 is a function of all the predictors, and so these values are embedded inside these columns, but there's not like a PC predictor A. So you get the principal components only and not the original predictors. So when we design our recipe steps, anything that happens after PCA has to say like select starts with PC, and that will select the components because we don't have the original variables anymore. Was there a question? Can you also how to do PLS with a recipe and compare model performance with PCA? I can tell you we don't have like a demonstration of it. You would just change this to step PLS. So for those of you who don't know, PLS stands for partial least squares. Actually, let me tell you about partial least squares in just a second. Let me defer that question for a second for good reason. I'll tell you, it's very, very similar to PCA, but let me explain that after a slide or two. Besides PLS, is there any other PCA questions about what it's doing or how we're doing it? Okay. Hunter had a question of like, is there a blog post about this? No, there's not, but Jared would know. At a previous New York Art Conference, the best PCA talk I was ever seen was given by this guy named Brian Lewis, where he used shadows as a way to show how this rotation works. And he actually had people in the audience stand up. He had a huge grow light that he walked around them with and showed how their shadows, depending on the angle at which he pointed it at the people, would have a wide distance between the shadows or a small distance. And he demonstrated PCA with that. I'm pretty sure that was recorded, and I'll ask Jared to find that and put it in the notes, because that was, and that's what prompted that animation is Brian's talk. So that I would definitely, if we can find that, I would definitely look at that as extremely good. PCA could be applied to any feature data. If we get 1,000 time series, we can get different PCA. Yeah, so as long as you have numeric data, you can apply PCA. You know, I wouldn't do it if I knew that the predictors were uncorrelated, because you're not really gaining anything. But you know, like financial time series, for example, would probably be pretty correlated. And so using PCA on those might be a good idea. Another question I get very often is, what about dummy variables? It's totally fine. It seems weird, but it's totally fine to do like step dummy, then normalize everything using step normalize, and then run step PCA. So the data going into PCA could be all purely numeric, and it could be a combination of dummy variables and so on. So you don't have to worry about doing it separately for dummy variables or anything like that. If you think the dummy variables are related or correlated with the other predictors, it's worth putting them in there. More questions? Anybody who's watching this video in the future is like, why is this guy pausing so long? Similar question, can you explain the difference between PCA and ICA? Okay, I'll do that in a minute too. Do you know that certain variables are highly correlated age and age group? Would it be preferable to filter one out pre-recipe or retain them? Yeah, let me also postpone this. Let me talk about general strategies here after I get through PCA. So let me go through the rest of PCA, and then I'll address each one of these questions and relate them back to PCA. Okay, so hopefully what I've done is I've told you that I've explained that PCA is really good for like dimension reduction when you have highly correlated predictors. And that could be very helpful for models like neural networks, support vector machines, even linear regression. And that using step PCA is how you would do that. And that you definitely want to normalize the predictors before giving them the step PCA. Those are the main takeaways. Now, about this data, there's one reason that this particular data set's a really good example for PCA. Is let's look at this plot, is we can really see like, yeah, principal component 1 captures almost all the variation of predictor A and B that they were originally made up this data, right? So the thing about the principal components are they only look at the predictors. They don't look at the outcome at all. And normally I would say like 90% of the time, even though PCA doesn't use the outcome, the principal components tend to be correlated with the outcome. But there's no guarantee of that because PCA does not use the outcomes at all. And this data set is a good counterexample, because if I take any vertical line and try to slice the data so that I have only class 1 on one side and class 2 on another, I can't do that. But if I take the less important component and less important to the original predictors and slice it around 0, I get really good separation between the blue and the red here. So this particular example I use a lot of times because it's a counterexample that says that, yeah, principal component 1 is most important to the predictors, but for this example, it's the least important to the outcome. So if I were to put this in logistic regression, for example, I would find that PCA1 has no effect on the classification accuracy. PC2 has all the effect. So you have to remember with PCA, the importance is all about the predictors and not about the outcome. And honestly, 90% of the time, those two things line up pretty well, but there's no guarantee that they do. So, so this is a good counterexample to that particular thing. So before I go on from here, before I get to PCA and ICA and filtering, any other PCA questions? Okay, so Oh, hold on. Sorry, there's more typing. I'm just waiting. Practically speaking, sometimes people use machine learning models to inform public policy decisions. What are your thoughts on these transformations with relation to predictors, since now the variables aren't directly represented in the model? That's another good question. Before I answer it, let me get my dog out of the room because she's supposed to be being walked right now. Come on, you want to go for a walk? All right, I'll address that one last. All right. Let the dog stay. Yes. Actually, you know what? Let me talk about that one first. How about these models? Since we're not using the actual predictors anymore, it in many cases it does limit interpretability, right? So if you have to explain this to somebody, there are some cases where you can get back to the original data. So if I were doing linear regression with PCA components as the predictors, linear regressions are just additive slopes and intercepts. PCA, it turns out, are linear combinations. So what I could do is, once I know what the weights of the predictors and the principal components are, since those are linear, and you put those into a linear model, I could back calculate the actual coefficients for the model that use PCA, but put them in the original predictors. So if you needed to say, like, well, the actual slope of predictor A was this, for linear regression or logistic regression, things like that, you could do that. Otherwise, what you'd have to do is do something like a variable importance score. Say, like, oh, we know that component number 13 was really important, and that component is, to the model, and that component is mostly associated with these predictors. So you could still do some explanation of the model, but it's like secondhand. So you'd be talking about the components and knowing what's important to the components, but it wouldn't be like, you couldn't say, like, the risk of this event happening increases by 7% with every unit of the original data. You couldn't say those really specific things. So that's the downside of it. But I'm not sure, there's not that many like machine learning models. They end up tending to be black boxes. So, whether you use PCA or not, sometimes the model itself is not that explainable. So they make sort of a tough situation worse, to be honest with you, from the perspective of interpretability. Okay. So PCA and ICA, what are or PLS and ICA? I'll start with ICA. ICA stands for Independent Component Analysis. It was originally developed in the engineering literature because what they were trying to do is, imagine being in a room where you have, in different places of the room, somebody's making a recording, but let's say, 20 people in the room speaking. So ICA was originally developed as a way to sort of deconvolute the signals coming from different sources. So you might have like 3 things that you're measuring, but there's 20 things that are going into each of those 3. And some people did the math. And the difference between ICA and PCA is, I mentioned that in PCA, the components are completely uncorrelated. In ICA, that you get to loosen that constraint a little bit, that they can have 0 covariance, but may not be uncorrelated. So it's a really small technical difference. And for many data sets, you don't see much difference between the PCA components and the ICA components, but there are some where you do. Let me give you a link. I didn't maybe explain that as best as I could. So we go through a bunch of these different these transformation methods like PCA and ICA in the book. And so Let me just put that in here. So if you want to read about like what we call linear projection methods, we compare principal component analysis to where's that? Principal component analysis to kernel principal component analysis, and we also talk about ICA here, and I'll explain PLS in a minute. But we do a lot of it's more thought out, just to be honest, in this book than it is probably with me explaining it. So I would suggest maybe going through the book and looking at the example, especially because it's a pretty good example, and look at the difference between these components and how they work. So let me try to explain PLS. So PLS. So I mentioned that PCA chases variation in the predictors, right? So PCA only looks at the predictors and is trying to maximize the variation in the first principal component. So from a mathematical perspective, what PCA does is it tries to maximize the variance in the first principal component. PLS is very similar, but it takes the outcome into account. So what PLS does is it also tries to maximize the variation of the first principal component, but at the same time it tries to do that at the same time where it's trying to maximize the correlation between the outcome and the first principal component. So PLS almost has like two criteria, whereas PCA only has one. PCA's only criteria is to maximize the predictor variance, whereas PLS does that and also maximize the correlation with the resulting component. So it's like a supervised method of PCA. It is also linear. And you can use it also as a pre-processing mechanism. In this particular case, there is something called PLS discriminant analysis, and that could be used when your outcome is categorical. So it's like a supervised version of PCA that the outcomes of it look like in their format and everything, you get new components back, but those components should be more aligned with the outcome instead of what PCA gives you. Now, how would you do that? For both like PCA or PLS and ICA, we have step methods for them. So step PLS is in there. It looks very similar to PCA, but you do have to tell it what the outcome is. So you have to give it the column that is in the outcome, and then you have to tell it how many components and things that you want, and then it gets it for you. One thing that I could point you towards is we updated how this works in recipes, and we did a blog post about it recently. So this outlines some of the new things that we did with PLS and how it works. So you can see an example, for example, of PLS here and how to use it. If you want to do ICA, as you might imagine, the name of that step is step ICA. Again, functionally, from the code perspective, it doesn't use the outcome, so you don't need to do that like you did with PLS, but you just give it the predictors you want to transform, and then you get them back. Instead of the new columns being PC1, they're IC1, and so on. So we have a bunch of different methods like this in recipes. That previous mentioned embed package has some more methods like this that are much more complicated. So there's also some things there. Let's see. What are the other questions? If you know that certain variables are highly correlated, would it preferable to be filter one out or retain them for PCA? That depends. So another thing that we do, and I don't think we have this as a hands-on exercise, but there's another one called step core. And what that does is you give it a threshold for correlation, and you say, give me the minimal number of predictors that their pairwise correlations are not above this threshold. Actually, we use this later in an example later on. So it's part of the notes that we'll go through. So when would you use that versus PCA? I try both of them a lot of times. So, the question about explainability, if you can get the correlation down and still get good performance, then this filtering method using step core is a better approach because you still have the original variables and you don't have to worry about interpretation. The downside is PCA or PLS may give you better performance. So you might have to sacrifice some performance that these steps would give you compared to what a filtering step like step core would give you. So I typically try them both and see which one, does better, and then see if it's a good trade-off. So, step core, if that can eliminate, 98 out of 100 predictors, and you keep the original units and the performance is good, then yeah, this is a much better approach for doing it. So it really depends on your data. But if you look at our original applied predictive modeling book, we try both in many of the examples that we have, both PCA and just simple filtering. Is there a way to use selectors to apply PCA to a subset of highly correlated predictors? Absolutely. So you would just do step PCA, in your recipe. Come on. You would do step PCA, X1, X2. You don't have to say all numeric. You can give it a list of the ones that you think should be in there. So you can sort of manually say, I want to run PCA on this subset. And I have had examples where I might do PCA twice. So I have different components for different subsets of predictors. That was a really weird example, but it was something I wanted to do, and you can do that here. I should also say there is a parameter here for prefix. So if I want this to be PCA of the X's, I can give the prefix, and this is what defines the new column names. So it doesn't have to be PC1, PC2. You could use this. So if you had some X's that you're going to do PCA on, and another step you have some Z's that you do it on, you could name them differently, so you don't have to worry about them, having the same name. Yeah. Okay. Any other questions about any of these methods? Some of you will be happy to know the dog did not want to go on a walk. She took him out. Dog didn't want to go anywhere, and she's back. So your encouragement made her stay. Factor analysis allows for rotations that relax requirement of orthogonality to varying degrees. Is it ever used in ML? Geez, I haven't thought about factor analysis since graduate school. I haven't seen it used that often. I think there are some cases where it's equivalent to PCA, but I don't know what those are. I will have to punt on that. I want to say I have seen it referred to, but I've never seen it actually used in any ML applications. In factor analysis is a little bit different in how it does the rotation. It's also like a linear rotation like ICA and PLS and PCA, but I honestly don't remember what the differences are, so I don't feel like I could explain it very well. I would maybe Google on that, because I don't know. How about something like set PCA, all core predictors threshold greater than 0.8? Yeah, no, we don't do that. What you would have to do is, yeah, I don't have a method of doing that. You'd have to predefine what predictors have the threshold above that. Is it a bad idea? No, I would say it's a bad idea. I would say that the thing I would think about is one of the downsides of step core is it does pairwise correlations. So very often when you have complicated relationships between predictors, the correlations are multidimensional. So step core might not find those, or might not effectively find which ones are the smallest subset. So a lot of times when we think about correlations, we think of them about two X and Y are correlated. But the notion of correlation is actually p-dimensional. It doesn't matter the dimensions. And I think And PCA would be able to do that. PCA can find the correlation in many dimensions as opposed to 2 dimensions. So PCA would be more effective at that. I don't know that using a threshold above 0.8 would capture like all the correlations. That's the only thing I would worry about in doing that. I wouldn't say it's a bad idea. The thing is about like predictive modeling, machine learning, is you try things, and if they don't work performance-wise, then it didn't work. There are some times I've done things, I'm like, oh, this will never work, and it does really well. So it's really hard to say ahead of time which things are going to work and which ones aren't. It's very dependent. So. Okay. All right, so this is a long section. We're almost there. It's 3:30. Since we have to switch rooms at 4, why don't I go for another 10 minutes and then we'll do like a 15-minute bio break, if that's cool. So I'll talk until 1:45, and then we'll take a break and we'll rejoin at 4 in the room number 3, I guess, the next room. So, okay. All right. So that's the end of the PCA section. I want to talk a little bit about how, if we were doing this sort of, we'll show you APIs where you don't have to do this, but if you were like doing your own recipes with like base R models and stuff like that, how would you do that? So let's talk a little bit about that. So here's some data. So it's a ggplot, back to the Ames data, and I'm plotting longitude versus sale price. So it's interesting. It's like a really nonlinear relationship, and there's clearly like patterns here, but it's weird, right? So it's like it's decreasing, and then it jumps up, and then it's decreasing again, and then it's kind of flat over here. Does anybody have an idea? Well, so here's longitude, here's latitude, and it's the same thing where like this looks like it has a big increasing slope, and then there's like nothing. And then it looks like it's decreasing, and then it's increasing again. Does anybody like have any ideas why these sort of like weird patterns are showing up? Breaks and slopes are different neighborhoods. That is part of it. Is there anything else that anybody wants to mention? Distance to amenities. Good guess. I don't think so. New versus older developments. That also might be part of it. The main reason we see these like weird divisions in the data is, let me go back to that leaflet plot I had for Ames. You know, one thing I didn't talk about at the when we talked about this yesterday is like, did anybody notice there's like nothing in here? Does anybody have any idea why there's like this dead zone of like no neighborhoods, or at least no recorded sale prices? Like maybe they didn't record these. Like, why would this be nothing in here, do you think? Oh, it could be a park. Yes, Travis got it. Iowa State University. So if like you zoom in, eventually you'll see things about like the University Boulevard, and so on. So there's no like public houses that you can buy inside the university campus, right? So what we're seeing is when we look east to west, so what we're going to see is this cluster of houses here are, where's the notes? Are this cluster here. And then, or actually it's from probably here to here. And then this cluster are things that are both above and below the university. So that would include these houses and these houses. So that those are making up like this bit here. And then this big decreasing bit here is data like mostly North Ames. So somebody said different neighborhoods, yes. That cloud I just showed you is much of these houses. And then remember like these ones that we had like way on the outside here? those are these sort of geographic outliers here and here, right? So this is east to west. And then the same thing happens north to south. So we have like a bunch of points and then almost nothing in between. That is these points. And then nothing in between is around here, like going up to down. So these points in Timberland would be these like dots right here. Okay. So it's, we're taking two-dimensional stuff. There's a big hole in the middle, and then we're looking at it in one-dimensional. And so, yeah, we are seeing these trends, and they're real trends, but they're very, very nonlinear trends. And so I think there's a lot of substance in here, but the question is like, well, how do we get at this substance? It's clearly not like a linear effect is going to be a great idea here, like one linear effect across the whole scale. So from like a feature engineering standpoint, we could do all sorts of things. We could find like the longitude and latitude cut points, these neighborhoods, and like fit a linear model in between them and things like that. A better way of doing it is using this thing called a spline. And if you've ever done geom smooth, what under the hood it's most likely using is this thing called a spline. And what a spline does is it takes one column of data and makes an algebraic sort of expansion of it into new dimensions. So it kind of creates like more features from that original predictor, and those features encode higher and higher dimensional patterns. So if I use a spline with 5 columns, that lets me account for a certain amount of nonlinearity in that original predictor. If I use a spline with 2 columns, that will allow me to do like quadratic, like think about it as like an exponent. If I have a spline in 50 dimensions, that means I can account for really, really, really subtle nonlinear features in the data. So what you can do is, if you want to see how this works, is you could just take these data and do a plot here where I'm saying, give me, so this in the spline, this is called a degree of freedom is the name of the parameter, but it's really related to how many spline columns I want to use. And BS stands for, don't get excited, it stands for B-spline. So if I want to be able to model like a lot of nonlinear terms, I might crank up the number of degrees of freedom to like 15, and you see it gets a lot more twisty and turny. But if I wanted it to be some nonlinear, but maybe not that nonlinear, I might choose a low value. And so the problem is you don't know what this should be, right? So I could make it 150, and maybe that's not the best of ideas. That's overfitting. You get this weirdness out here. What's that about? Splines do really, really weird things in the extremes. So especially if you have any data that are outside of the mainstream on the edges of the distribution, the variance associated with the splines like blows up. And it's clearly like overfitting here. And it's probably like overfitting in here too. So what I'm doing here is I'm using step geom to get a sense of like just ballparking, like how nonlinear, if I were to like use longitude and latitude with splines, like how, I don't know, how smooth or how nonlinear should they be? And we'll do this in model tuning, but if you were just doing it visually, what you might do is you just might kick this around until you're like, I don't know, what does like 15 look like? I'm like, oh, okay, that doesn't seem like it's overfitting really, but it's maybe missing maybe some nonlinearities here. You might say like, what does 20 look like? And then just kick this around until you feel like you've got something that is probably nonlinear enough, but not doing crazy things. So this is like what I called eyeball tuning, where you're just like looking at it and say, oh, that looks great, and it's very subjective. So it turns out that splines are very effective. If you were to plot these, I found that anything from like 20 to 5 degrees of freedom probably worked fairly well here. I'm going to use a different type of spline than what I just showed you, something called a natural spline, which is a little bit better. And I'll use 5 degrees of freedom to account for nonlinearity. So this is a recipe that we'll come back to after the break. It's just like an example recipe. What I did is I took some other predictors that I know are important. We haven't talked about, like building type, general living area, number of bathrooms, and things like that. Lot area and general living area, we noticed on the first day are very right skewed. And so I'm going to use boxcox to estimate an appropriate transformation of those. Here's my step other for neighborhood. And then I convert those neighborhood values and building type and a few other things here to dummy variables. Here's the interaction that we identified. And then I'm going to model longitude and latitude using splines with 5 degrees of freedom. And so you can do a lot more with the Ames data here. But this is the one we'll talk about for a couple more slides and show how you would use this with LM and some other stuff. So we'll stop here because it's time for the break, and we'll come back to this recipe and talk about like how we model with it. Yeah, somebody method eyeball tuning. I actually had a professor that kept using something he called OEM, and we were like, what does that mean? And then somebody finally had the nerve to ask him, and he said it's the old eyeball method. So he would say, well, OEM, it's probably about like 5 degrees of freedom. We're like, what is he talking about? He's basically like looking at it and used a fancy term for it. So, okay, thank you. We'll stop here. If you have other questions in the break, post them here and I'll answer them when we come back. So we'll come back at 4, and I believe it will be, and Jared, correct me if I'm wrong, we'll go into break or room 3, I think, I guess.
That sounds about right. I'm not sure we're supposed to be in 3 right now, if we're supposed to go into 4. And if we are supposed to be in 3 right now, that means we didn't get kicked out. Just go to the schedule and go. It is highlighted in the schedule what room you're supposed to be in at that moment. Okay. So we'll do our best to follow that. Yep, still figuring this out.
All right, we'll see you in 15 minutes.
Yep.